Hey guys, today I'm going to show you how I built this 51.2 volt 78 amp hour lithium iron phosphate battery in a steel toolbox. This is the toolbox I'll be using for this build. It is Husky brand from Home Depot and it's metal with a nice tread plate finish. It measures 20 inches wide, 9.7 inches deep, and 8.9 inches in height, and is rated for up to 100 pounds. Very spacious. It's pretty much just a metal box. There was a plastic tray to put tools in the top here, which I took out because that's not needed. For the batteries, I'll be using these 6 amp hour lithium iron phosphate cells that I purchased from Battery Hookup. These are 32 650 cells, meaning they're 32 millimeters in width and 65 millimeters in length. They are 3.2 volts nominal, 3.65 volts full charge, and 2.5 volts fully discharged. If you like what you see with these cells throughout this project, and you want to purchase some for your own project, you can use the discount code BATTERY, which will take 5% off, and also let them know that I referred you. Now for assembling these cells, I'm going to use the standard 1x3 clips, and the way this works is you simply insert your cell, and then you'll have an accompanying clip on the top, and this will hold to form your battery bank. So these have little notches here on the top, and you can connect these together to form any configuration you want. So what I need to do is figure out the optimal configuration so I can fit as many cells in this toolbox as possible. So I calculated that I can fit as many as 6 cells in here, so this would be the height of the 6th row before I can no longer close the lid. Additionally, I can fit 13 cells in width. Next, I calculated that I can fit 3 cells in the depth direction of the box. So that resulted in the configuration of cell holders you see in front of me here. I have 2 holders that measure 6 by 13, and then I have a third holder that measures 4 by 13. So that will give us the 6, 12, and 16S we need to reach 48 volts. Now before I start putting all of these cells into these holders, I want to add a bit of extra protection on the positive end. So the way these cells work is, this is the negative terminal obviously, but what a lot of people don't realize is that the negative casing continues the entire way of the cell up until this black ring. So you see in the top end here there's a black ring around. This whole area is going to be negative. And then you have your positive terminal that sits right in the front. When you're running wire or your nickel strip across here, the only thing that separates that nickel is this piece of heat shrink and this little paper disc they install. So what I want to do is add a separate level of protection to minimize the chance of any nickel or wire rubbing through this insulative layer on the cell. And to do that, I purchased some of these green adhesive discs. These are insulative discs specifically designed for 32 650 cells. You simply peel the disc off, and then you stick it right on top of your cell. So now you can see there's an extra additional layer of safety to prevent any wire or anything from rubbing through into the negative casing of this cell. So now we're ready to begin populating our cell holder. So the easiest way to explain this holder is 13 wide. So the first row here is going to be all the same polarity. The second row will be reverse polarity, and they'll be connected in series. So each of these 6 rows will be connected in series, and this will form a 6S 13P battery pack, which will be connected in series with the other 2 battery packs to form the full 16S system. So the first cell is going to go positive end up. The second cell will go positive end down, positive up, positive down, positive up, and positive down. So I'm going to follow this same pattern the entire way across the cell holder. And now I'm ready to put the top piece on. Sometimes this takes a little bit of work to get all the cells lined up perfectly here. So this is the nickel strip I will be using to spot weld these batteries together. So it comes in a roll like this. It's 0.2 millimeters in thickness, and it's specifically made for 32 650 batteries and these particular cell holders. I cut it perfectly flat on one end, and then on the other end I have 2 tabs cut sticking off. I cut it using a pair of straight tin snips. These work very well on it. You might be able to cut it with regular scissors. So the purpose of these tabs is I'm going to use these to solder the BMS leads to once I get to that step later in the process. Now I only need one of these tabs left, so I'm just going to snip off the second one and lay the nickel strip right across the cells here. And you can see how that lays perfectly flat across the top of these cells. It's a very nice design. So then on the leftmost side of the cell, You can see where the tab is going to stick over the end. I'm just going to bend that down flat for right now. So for the spot weld here, I have a Sunco 709AD. This is the 240 volt version, since there are numerous issues with the 120 volt version. I've also modified this particular spot welder with a pair of custom electrodes. So this is 4 gauge stranded welding cable, and then I've just got some 6 gauge solid copper I used for electrodes and filed the points down. So for welding the 0.2 millimeter, I'm turning the current the entire way up to 8, and I'm going to set it for a pulse of 12. Alright, now the nickel strip has this little notch cut in it where the cell is. And that's so that you can put one electrode on one side, and then the other electrode goes on the other side of that notch. And the reason for this notch is that helps prevent the current from going straight across, because now it has to go down through the nickel into the cell and then back up the other side. And I'm going to probably put 6 or 8 welds on each cell. I'm not sure here. Let's see how many I can fit. So just getting a closer look at these welds, you can see they are a little dark, so maybe I can turn the current down a little bit, but I'd rather have them stronger than not strong enough. So I'll just proceed up doing the same thing on all of the cells. Alright, so the first piece of nickel strip is welded completely. Now after about halfway through these welds, I did turn the welder down to a pulse of 8 instead of a pulse of 12. And it was right around this point, I believe. So you can see some of these welds are a little bit lighter than the rest. It's a fine balance of just trying to find the right point where you're not, over welding and punching holes through, but you're making sure you have good contact and it's not going to come back off. I'm ready to lay the next nickel strip down and begin spot welding for the next connection. These batteries do have energy stored in them, even though they're not fully charged yet, and I want to make sure there are no accidents that can cause a short circuit while I'm welding this. So I'm going to take some of this Kapton tape. It's just a very thin film, high temperature tape. So you can see how the tape helps cover up some of the exposed metal. It doesn't necessarily cover the entire surface area of both cells. Some of the negative of the first row is still exposed. However, it does assist in preventing accidental shorts as you're working on the battery pack. Alright, so I completed the spot welding on this battery. The top has 2 strips, and on the bottom there are 3 connections, 3 strips to spot weld on. So we'll talk about how we're going to wire the positive and the negative terminals later, but if I did everything correctly thus far, I should be seeing voltage, and I've got 19.77 volts. Alright, so it's been several weeks since I started this project, and I finally have some time to get back to it. So where I left off is I have all 3 battery packs spot welded. So one thing I have to consider here, because this is an even number of cells, there are 6 cells in series. So that means both the positive and the negative end up on the same side of the battery pack. So to connect these 2 battery packs in series, I have 2 options. I can situate the 2 battery packs such that the positive and negative connections are facing each other, or I can situate them like this such that the positive and negatives are pointing towards the outside of the battery packs. So I think this is the way I'm going to do it. So what I'll need to do is take some wire and run it from the top of the battery pack over to the second battery pack to complete these series connections. So when I go to press these 2 packs together, I need to make sure that they are not shorting out because there's all this metal here, but I can't rely on the Kapton tape alone to prevent a short circuit. So I picked up some of this paper on Amazon. I believe it was called barley paper, and it's just adhesive paper that is typically used in building these batteries. So I'm going to roll a sheet out on top of this one, and then I'm going to roll a sheet out on top of this one. That way I have a double insulative layer of this paper. This stuff really wants to roll itself back up here. So it's got this backing you just peel off. And that didn't quite make it the entire width of the battery pack, so I just cut a thin piece to cover up that at the top there. Lay that down as well. Now that that's completed, I have 2 very nice insulated battery packs here. Almost looks as good as a professionally built battery. So I can stand this one up. And I can safely push them together. And there we go. But because safety is very important to me, I'm also going to insert a piece of plastic cutting mat between the 2 of these. So this is 1/32 inch thick. So now I have a plastic insulator in addition to 2 pieces of the barley paper between these batteries. So one thing I also wanted to make sure of when I push these two together is that these BMS tabs are offset. So you can see this tab goes with this pack, and then this tab goes with this pack, and so forth. I want to make sure these are not parallel with each other such that there's a tab here and a tab here, and then when you push these together, these two tabs short out. I made sure that as I built this pack that these tabs were cut such that they were offset when I pushed the two together. Alright, so I'm now at the step where I need to join the positive from this battery pack to the negative of the opposing battery pack to form the series connection. And to do that, I'll be using 3 pieces of number 12 silicone wire. Now one piece of number 12 is good for 20 amps when following the NEC recommendations for home residential wiring, so I'll just space them out evenly like you see here. And then I'll weld a piece of nickel straight across and solder them to that nickel. Alright, so now I've measured and cut a piece of nickel strip, but obviously this is too wide and I don't need it to be too wide. So I'm just going to take my pair of scissors and cut it right down the middle, and then I'll have a piece for each side that I can solder to. So I'm laying that over the cells, going to count 4 cells in and make a mark, 4 cells in from the other side and make a mark, and then right in the middle of those make a third mark. So those 3 locations which I've marked off is where I'm going to solder my series connections. Alright, so as I was going through and soldering these connections, I decided I was just going to do 5 pieces instead of 3, really just to minimize the voltage drop across each conductor. You can see how I soldered it here. I made sure to get the joints nice and hot, that way the solder is properly adhered to both the wire and the nickel. So now I can set this down over top of the battery pack like so. And then when I'm ready, all I have to do is spot weld this strip into place and my series connections are done. Now unfortunately I can't do the same trick from the second pack to the third pack using the wire and the spot weld. The opening on this toolbox is about 1/4 of an inch short of the total width of those 3 battery packs. Now that's not a problem, I can still fit it in because you see there's this lip here, which is not a problem because that third battery pack will slide underneath of that lip. But that just means that I have to put the battery packs in as 2 separate pieces, not as 1. So to do that, I'm going to put a piece of strip across here, just like I did in the other battery pack, and then run 4 pieces of this red wire, and just use a pair of XT60 connectors. That way I can set this battery pack in first, then set it in the larger battery pack, and then combine the 2 with the XT60 connectors. Now I really did not want any mechanical connections like this inside the battery, but that's the only way I can see this working for this particular scenario. Alright, so I got my 2 sets of nickel strip here. So you can see it's just the 1 wide, and then I soldered 4 number 12s on, so I got 2 number 12s on one end, and 2 number 12s on the other end. And those number 12s go up to an XT60 connector, which I've soldered on and heat shrinked nicely. And in doing this, you'll notice there's 2 different length wires here. So on the opposing piece, I have the same, except I have the shorter wire here going to the longer wire on the other pack and vice versa. That way I'm certain that all 4 wires are the exact same length. So here's the larger of the 2 battery packs, and you can see the XT60s down there. That will join to the smaller pack. You can see where I welded on this strip with the 5 conductors that will join this side of the battery pack to the other side of the battery pack. So this is the main negative side down here. This is the side that will be facing away or outside of the toolbox. So I want to cover this as well with some more barley paper. And then the top of this part here where the first connection is actually of particular concern because this part is going to be butted up against the lip of the toolbox. So I want to make sure there's an extra protective layer there. So I'm going to have this strip of barley paper I'm going to place over and then fold down. Just to make sure there is no risk of anything rubbing through the insulation here. Just apply that like so. Alright, so with the battery pack stood back up, I have this very large blue heat shrink I'm going to put the entire way around the battery pack. Now this was left over from a previous project, so unfortunately it really needs to be about 2 inches longer. So I'm probably going to have to apply a second piece just to cover up some of the edges here, but we'll see how this works. Yeah, that was not easy getting that in there. So it is in there. Let's go ahead and shrink it down now. Alright, so there we go. Like I said, the heat shrink is a little bit too short because it was cut for a different project with different specifications. But it looks very, very nice now that that's completed. And one of the biggest reasons I love using this full pack shrink, not only does it add safety on the sides for reducing the amount of contactable surface, the compression that squeezes these batteries together, you can now pick this up and move it around as one solid block. It's no longer fragile, flopping around or anything like that. So that is a huge win to this full pack shrink in my opinion. Alright, so putting the battery packs aside for a moment, we now need to talk a little bit about the toolbox itself. So I'm planning to have the positive and negative connections come out the left panel here. And to do that, I picked up these thumb screw posts. So what you do is you take off this here. So we're going to drill a hole that's the diameter of the centerpiece you see here. So then our bolt will stick through that. Then we'll stick it through the hole in the toolbox. And then on the outside, we'll put this piece over. So you can see there's now a protective piece of plastic that prevents this bar from making contact with the toolbox. So looking at the drill bits I have, I believe I'll need to make a 7/16 inch hole. So now I should be able to put this piece through from the back. Let's see. There we go, just barely fits. That was a perfect size hole. So now I can put through the bolt. And then we have this piece here, which has a cutout for the nut that will face outside, away from the toolbox. And then we simply thread on the nut. And there we go, we have our first battery stud. So I'll just have to do the positive the exact same way. And there's the red post as well. Alright, so this is the BMS I'll be using for this battery. And this is the BMS that Battery Hookup sells. It is a 16S lithium iron phosphate 60 amp BMS. Unfortunately, the 16S is only available in 60 amps, while most of their other BMSs are available in 100 amps. So this is a common port version, which means you have one lead that goes to your battery. The black lead marked C- will do both your charging and your discharging. That's the common port. Additionally, we have a temperature sensor here, which we can attach to our battery. And this sensor will prevent our battery from charging below freezing, because lithium iron phosphate cannot charge below freezing, or it will be permanently damaged. I also purchased this little Bluetooth dongle module, which plugs into the BMS and will allow us to see specifications of the BMS, and I think you can even change some settings from your phone. There's an app you can use for this. However, I did notice that the connector on the dongle and the connector that's on this BMS are different sizes, so this connector will not fit. I did reach out to Battery Hookup about this, and they responded very quickly. And basically asked if I can just cut this connector off and solder wires to this BMS, and they said yes. On the bottom of this BMS, you can see there is ground, TX, RX, and V bus, which is your voltage positive. And if I look at the battery here, I can also see ground, RX, TX, and VDD, which is voltage positive. So I'll solder the ground to the ground and the V bus to the VDD, obviously. Then for the TX and RX, they will be swapped. So the TX on the Bluetooth will go to the RX on the BMS, and the RX on the Bluetooth will go to the TX on the BMS. Alright, so I took the panel off the bottom of my BMS to solder on my Bluetooth module leads. So this gives us an opportunity to see what's under here. Up here are the FETs to turn on and off. A couple diodes over there, not quite sure what they're for. And here's where I attach the Bluetooth leads, and then I cover them in a little bit of hot glue for some insulation. Alright, so next I'm taking the two black leads that are marked C-, and they come pre-tinned, but I don't need these pre-tinned ends on here, so I'm just going to cut the end of those off. And then I stripped off, I don't know, about a ½ inch of insulation here. So I use these open barrel lugs whenever I can. I really like the way they come out. So this one is a 60 amp, and then I'm also using a piece of heat shrink here. Slide the heat shrink on first. And for crimping, I have this IWIS, it's an IWS 5100A tool, and you can see one of the crimpers is marked 50 to 60 amps. And I've applied a little bit of pressure on it, so not so it's crimping, but just so the tool is holding the lug. Insert both of my wires, trying to keep them the same length here. It takes a lot of force to crimp these open barrel style plugs, pretty much your whole body weight you have to put into it. Alright. Like I said, that takes a lot of force, but you get a very, very nice crimp out of that. Alright, so now we need to talk a little bit about the BMS harness wiring. And these are the individual balance leads that will go from the battery pack to the BMS. Now there are two of them. There's a white connector and a black connector. On the front of the BMS, we can see where the white and black connect. On the side there, I don't know if you can see, it says B0, and then we see a B10, a B11, all the way up to a B20. So this is designed for up to a 20S system, we have 16S, and you see they clipped out some of the wires in the middle there for us. So this black wire will go to the first connection, which is the main negative of the battery pack, and then we'll work our way up with the white wires going to connection 1, connection 2, and so forth, until we end up all the way on the black connector. So if you remember earlier on, we left tabs sticking out the side here, where we're going to solder these balance leads. Now it's very important that these balance leads are in the correct order, otherwise you risk damaging your BMS or it's just not going to function properly. So what I want to do here is just make sure the order of these. So checking the first connection, we have 3 volts, 6 volts, 9 volts, 13, 16, 19, 23, 26, 29, 32, 36, and 39. So I'm going to solder those wires in the order I just showed you. Alright, so you see I have quite a mess of wires here soldered on. I'm going to try to clean up some of these and bundle them nicely, but before I do that, I want to go through each pin here and just make sure I have these connected correctly and in the correct order. This wiring harness is a bit different than some of the ones I've used in the past because it has 2 connectors and it has 2 red wires and 2 black wires. And next I'm going to go through this connector pin by pin and just check. I should see the voltage increment by 1 cell each time. So the first pin is 0 because it's negative. Then I see 3, 6. So I now know these leads are in the correct order and they're ready to plug into my BMS. So on the main positive battery pack, there's 3 12-gauge wires that come out. So I'll be crimping on another 60 amp ring terminal, which will go to the positive post of the toolbox. So you can see the crimp on these 3 number 12s here. I really like that B-style crimper. Much better than messing around with that hydraulic tool I have and gives a better look. Alright, so I've got one more connection I need to make, and that is joining the 3 main negative number 12 wires to the 2 number 10 wires coming out of the BMS. And to do that, I have the 6-gauge copper butt splice. Now there will be a lot of exposed copper here, so I'll use 2 pieces of heat shrink to insulate this when we're done. And to crimp this splice, I have a Dentalion brand crimping tool. Insert the splice into the largest slot here. Insert both of my conductors. Okay, and there we have a nice crimp that is not going to come back out. So I just need to do the same on the battery side of the splice. And there you can see the second connection as well, perfect. And here's a look at the splice with the heat shrink nicely installed. Alright, so now we're up to the difficult part, and that is transferring this battery into this toolbox. That larger one is very heavy. It's got to be about 45 to 50 pounds, so I'm not sure how I'm going to lift that into here carefully, but we're certainly going to give it a try and see if we can get this done in an easy fashion. I did tape this BMS to the top just so it's not flopping around as we're moving this, and I also covered both the negative and the positive terminal just to reduce the amount of exposed metal. So first the small pack goes in. Alright, so I ended up using a piece of tie-down strap here, so I'm hoping I can use this to lift this battery into place and then pull the strap out from underneath of it. We'll see if that works. Alright, so the battery pack is in, and that was not easy. I ended up having to have my wife come out and push the bottom piece so it cleared the first pack. Then I was able to set it down with the straps, and then I simply pulled the straps out from underneath. So the straps work themselves, it's just that this is a heavy bulky object and there's really nowhere to put your fingers down in here because it's tight on both sides. But then I also did a few other things while the camera was off. I have the XT60 connected. I neatened up some of the BMS wires a little bit, so they all come straight up the front. I have them held down in groups here with zip ties and kept on tape. I kind of coiled them up a little bit because they're all different lengths. I really should have trimmed them to fit, but I wanted to make sure I had the longest possible conductors because I knew I'd have to be placing these batteries in here separately. I also mounted the BMS down in there and attached the main negative and the main positive to the appropriate posts. And the BMS is just held in place with a zip tie through 2 holes I drilled. So now that we're all caught up there, we're ready to plug in the balance connectors here. On this particular BMS, remember pins 1 through 10 were on the white connector, and then pins 11 through 20 were on the black connector. So we want to make sure we're plugging in the white connector first. Okay, and now we can plug in the black connector. Perfect. So now if everything is connected as it should be, we should see full pack voltage on these terminals in the front. 52.8 volts, alright. So lastly, we have this little temperature sensor left here, and I want to make sure this is positioned on the battery so it's picking up temperature of the batteries. Fish it under the shrink wrap here, that way it's against the batteries and picking up temperature inside the shrink wrapped battery pack. And then just a small zip tie to hold that in place with the rest of the bundle of wires. So we have one connector left here that has not been connected. This is for our Bluetooth module. So I'll go ahead and plug that in. Now I want to do a final check and make sure I can close this and nothing is being obstructed. And just checking the final weight on this battery, it weighs in at 81.3 pounds. Alright, so trying to get this Bluetooth to connect has been an interesting experience. I have a Samsung Galaxy S10 Android smartphone. The app, when I installed it, said it was built for an older version of Android, and it was able to discover the Bluetooth BMS, but when I tried to connect to it, it kept saying failed to get data, or something to that extent. So I ended up taking a very old iPhone I had laying around. This is an SE, I believe, and you can see it's the app on the top right there. I'm not sure how you pronounce it. Just download it from the App Store. So instantly it picks up on the BMS, you click it. So here's all the data. You can see the individual cell voltages, all 16 of them there. Manufacture date was December of 2020. The app is free to do what you see me doing here to view this information. If you want to configure it, you have to pay $5.99 for the configuration portion, which will write data to your BMS. I went ahead and purchased that, so now I can click on the config button. And I'm going to go over to BMS settings down here and BMS read. So what that's doing is pulling in all the settings on this BMS that are predefined. So it's set for a number of cells of 16. Cell full voltage is 3.55 volts. So I want to change this to 3.65 to match the specifications of my battery. Cell minimal voltage is 2.9. I want to change that to 2.5. So the balance voltage, it's going to begin balancing the batteries at 3.4 volts, which is fine. Balancer enabled, only enabled when charging. So that way you can uncheck this to continue balancing after charging ends. So when that's complete, I'll click BMS write. Continue writing BMS config, yes. And I see a countdown occurring at the top there, it's doing something. Alright, so to charge this battery up for capacity testing, I have this Battery Evo brand switching power supply from BigBattery.com, and this is a 58.8 volt 17 amp power supply charger. I'm just going to leave this charger run until the BMS in this battery shuts it off, and hopefully it's done some balancing by that point. And we're charging. We're putting in 930 watts to this battery. Alright, so we're finished with the initial balance of this battery. Now this took a long time to balance because this BMS only has a 50 milliamp balance current. So I actually ended up using the iCharger X6 to charge up the individual pairs. I think I spent about 3 or 4 days trying to get this balanced. Anyway, I have my typical capacity testing setup connected here. And for those of you who are not familiar with it, the negative comes out, goes to a circuit breaker. It's going to this Batterium shunt over here, then it's going into the inverter. The positive lead is coming straight out of the battery to the inverter. There's a small pigtail wire here going from the shunt to the main positive for the voltage sense. This shunt connects to a Batterium off camera and transmits data to this display. We can monitor voltage, amperage, wattage, amp hours, and watt hours. For the load, I have the standard Lasco space heater. When run on low, it consumes approximately 950 watts, which should put a 0.25 C load on this battery. Plug in, breaker on, inverter on. Alright, it looks like we've settled around 994 watts, so we'll let this run until either the BMS low voltage disconnect or the inverter low voltage disconnect shuts it down. Alright, we're nearing the end of our test here and we're just close to 74 amp hours. I think we're going to come up a little bit short. Looking at the BMS readouts here, you can see the first 8 cells are all around 2.9 volts, and as we get towards the end, they're around 2.8 to 2.7. So I definitely think this battery would benefit from some more balancing at the top end here. And there we go. The BMS is reading cell under voltage protection and it shut down our test. And the final capacity readout is 74.76 amp hours, just 1 amp hour short. So there we go. I hope you enjoyed this video. This took a significant amount of time to put together, film, and edit. So if you don't mind, please hit that like button down below. If you decide to purchase any of these cells, again, please use discount code BATTERY, which will take 5% off your order and let them know I referred you. And thanks for watching.